Okay, this is 2.2.1, the photoelectric effect. Now, the idea behind today's lesson is the wave-particle duality of light, which basically means that previously, in your GCSE studies, you thought of light as a wave. But now we're going to see that actually light is neither a wave nor a particle, but actually behaves like both. And it chooses when to behave like either of them. So this discovery actually led to Albert Einstein gaining a Nobel Prize. He didn't gain a Nobel Prize in his work on relativity, he actually gained a Nobel Prize on the photoelectric effect. So we start with an equipment called the gold leaf electroscope. And the gold leaf electroscope has a zinc plate at the top. And then it has a metal bar that runs down. And a gold leaf. Now, we use a gold leaf because gold can be made very, very thin by rolling it out. And under normal circumstances, that gold leaf that hangs off the edge of that metal bar will basically be completely vertical. Because under gravity, if I hold like a piece of foil up, it will hang vertically. So what we do is we charge this plate up with excess electrons. So this all becomes negatively charged, all along there, including the gold leaf. If the bar and the gold leaf are both negatively charged, what happens? They repel. So that's what causes the gold leaf to sort of move outwards and have this gap between the bar and itself. Over here they're fixed together, so it's attached over there. So that's why it doesn't just fly off, it's attached at this point here. But the rest of it, it basically just repels and it causes the gold leaf to hang at some angle. Yes?
So you know the gold leaf initially, before it's charged, is it parallel to the bar?
Yes, so before it's charged, the gold leaf hangs vertically and is parallel to that bar. Yeah? And then for this experiment, what we then do is we shine some light onto that zinc plate and then we observe what happens. Now this experiment is evidence that light behaves like a particle. This experiment gives us evidence that light behaves like a particle. And we call that a photon. Put a box around that because you need to know this as fact.
So the zinc plate has current flowing through it, and it passes down.
No, so there is no current. What we do is we will connect it up. We can charge it up in any way we like. But essentially we charge it with excess electrons. We store a charge on it, and then it's not connected to anything. Because if it was connected to something, like ground, then there'll be a current flowing through. So the idea is it's isolated so current cannot flow. It's statically charged.
So what is charged? The golden leaf and the zinc plate?
The whole thing. The whole thing has a negative charge.
So that bar is just metal?
Yes.
It's element?
Yeah. So just charged up. Yeah? So now we want to look at what happened in this experiment. So, light. It's not a wave. It's not a particle. It has wave-particle duality. But let's assume we don't know that yet. Because prior to this experiment, we don't know that light behaves like a particle. We say that light is a wave, an electromagnetic wave. So light has a wavelength. Light has a frequency. We can shine light for some time, a long time or a short time. So when this experiment was conducted, what they found was that below a certain frequency, nothing happened. So there was a certain frequency of light. Below that frequency, nothing at all happened. But above that threshold frequency, the gold leaf collapsed and became parallel with the bar. So that tells us that above some certain frequency, that gold leaf electroscope lost its charge. And so gravity took over and made that gold leaf parallel. So let's capture this. Below a certain threshold frequency, threshold means minimum, nothing happened. At a higher frequency than the threshold, the gold leaf collapsed. So this had to be explained in some way. They did this experiment in several different ways. So they thought, okay, so frequency has got something to do with energy then, because if the charge is being lost, then that means that the excess electrons that were on the surface of the gold leaf electroscope must have been lost. Now, if the system was isolated, the electrons aren't going to flow into something like ground. They're going to have to leave the material and fly away. So they tried this out several different ways. So they adjusted the frequencies. They saw that above a certain frequency, the charge was disappearing and the gold leaf was collapsing. Below a certain frequency, it was not happening. They tried the lower frequencies for a longer amount of time, thinking that if we were to shine this light for a longer amount of time, it will keep absorbing energy from the light until the accumulated energy is enough that the electrons will leave. However, nothing happened. They saw that this phenomenon was occurring with no time delay. The moment that light was incident on the material, that's the moment that the gold leaf collapsed. So it's instantaneous. There's no time delay. So there was only one way to explain this, and that was not using the wave model. So we model the electrons on the surface of this material as living inside an energy well. They're bound by some energy to this material. So here's an electron living in its energy well. and some photon comes along. This is an ultraviolet photon. Now this electron, one electron, absorbed that one photon. And if the energy of that photon was great enough, it allowed the electron to escape that energy well, jump out of it. And whatever energy it had excess left over would then transfer to becoming kinetic energy for that electron. So one electron absorbed one photon. If the energy of the photon was great enough, the electron would escape its energy well. So this means that the photon has to have enough energy. Let's put a box around that entire statement, as you'll need to learn this. Yes. Say again? UV is also light. So you're talking about visible light. The frequency of visible light is less than the frequency of UV.
Also, light can be.
Okay,
So where?
let's talk about the electromagnetic spectrum. Gamma, X-ray, UV, visible light, infrared, microwave, radio wave. All of these live on the electromagnetic spectrum. Think of them as all the same thing at different frequencies.
So they're all light.
They are all the same thing at different frequencies. Just like you have sound at different frequencies. Treat all of these things as light at different frequencies. They're all basically, either you use the electromagnetic spectrum, so they're all electromagnetic waves as a model, or you use the photon model. Either way, they're all either electromagnetic waves or they're all photons. So they are all the same thing at different frequencies. So UV has a higher frequency than visible light. That means that each photon of UV carries more energy than each photon of visible light. Including within visible light, each photon of blue light carries more energy than each photon of red light. Yeah? Say again?
Because blue light has a high frequency.
Yes, because blue light has a high frequency. Right, let's turn a page. So we'll add the statement that any energy that was left over from the photon turns into kinetic energy from the electron. Now we generally use metals for this experiment because metals have a shallow energy well. It means that it doesn't take much energy to make these electrons leave the material. Metals have a shallow energy well, so it does not take for electrons to escape. Now let's think about it. Couldn't electrons from the surface of our bodies, for example, also leave in the same way?
Oh, so we get like what do you call it, sunburn? What's that?
No.
The light.
So sunburn happens when the UV is absorbed by your skin. That usually happens because there's a raise in temperature of your skin.
So is it because the energy well of your skin is like there's a higher energy well?
Okay, so yes, the energy well of your skin is a deeper energy well. That's correct. So it takes more energy.
So what exactly is energy well?
It's the amount of energy that the electron is bound by to that material. For example, let's think of Earth. If you want to escape the Earth's gravitational field, it takes a certain amount of energy to escape it. Well, how do we do that work? Well, we take rocket fuel and we burn it. And we use that energy from that fuel to escape the Earth's gravitational field. Right, well, something is also binding those electrons to that material. Well, okay, if the electrons want to escape the material, a certain amount of work must be done. Yeah? Now, actually, it can happen in humans as well. Ionization, ionizing radiation. Gamma photons have enough energy to ionize your cells. So, if gamma photons are incident on you, well, gamma photons have enough frequency, therefore have enough energy to make those electrons absorb it, and then they then have enough energy to escape you, causing ionization. So it can happen in humans, can happen in organic matter. However, it takes much more energy. And that's why you don't get ionized by radio waves, microwaves, as some people would believe. You don't get ionized by visible light. So light for humans, or photons, really start to become ionizing beyond X-rays. X-rays not so much, gamma rays a lot more. Right, let's construct a table then that compares two different theories of light. We'll do the photon theory and we'll do the wave theory. We'll see how they compare in their predictions for the behavior of the gold leaf electroscope under these conditions. And then we'll see what actually happened. Okay? So, we'll write photon theory. And wave theory. So the photon theory predicts that nothing will happen below a certain threshold frequency. The wave theory says that any frequency should be able to liberate photoelectrons. Now we start calling these photoelectrons because they have been liberated from their material or from their atoms through the use of photons or through the use of light. So photoelectron just basically means electrons that have been liberated by light.
So photoelectrons are electrons that have been like.
Photoelectrons are electrons that have been liberated by light or by photons. Yes. So when they've escaped, we call them photoelectrons. Hence why this is called the photoelectric effect. So, photon theory says nothing will happen below a certain threshold frequency. Wave theory says that any frequency can liberate photoelectrons. There's a secondary point to add to that, is that electrons are liberated instantly in the photon theory. So electrons are liberated instantly. And in the wave theory, there is a time delay. Before electrons are liberated. Now, the first 2 points go hand in hand. So if we look at the wave theory, there is a time delay because any frequency can liberate them. That means that a continuous wave of this thing we call the electromagnetic wave is being absorbed, and until enough energy has been absorbed by the electron, which takes some time, then the electron will liberate. Which basically means that if you have red light, it will still liberate the photoelectrons in the wave theory, given that you've given it enough time to absorb all that energy. But blue light or UV light will liberate them faster. What actually was shown in the experiment is that it happened instantly, and it only happened for a minimum frequency called a threshold frequency or above. So this happened in real life, this happened in real life, this did not happen, this did not happen.
So is that only because they tested it at the minimum frequency?
No, they did it at loads of different frequencies.
But nothing happened.
So if you did it at a lower frequency, nothing happened. If you left that light on for hours and hours, nothing still happened. So nothing changed. Doesn't matter how long you kept the light on for, doesn't matter if you increased the brightness, nothing happened.
In the wave theory, it's like, I know it's wrong, yeah, or is it wrong?
Well, you haven't asked the question yet.
So like, is it like the energy in the electron builds up until a certain amount and then it's free?
Yes, so in the wave theory, the electron is constantly absorbing this wave. So think of it as a continuous wave that keeps getting absorbed by the electron. Yeah, the wave keeps going into the electron until the electron's gained enough energy from it to jump out and leave. So that's what the wave theory says. But that's not what happened in real life. Now, the photon theory also says that the kinetic energy of electrons depended on the frequency of the light. So if the frequency was even greater than the threshold, whatever excess energy was left over was used as kinetic energy. It was not to do with the brightness of the light. So the brightness, also known as the intensity. Let's think about what this means. Changing the frequency changes what feature of the light? Well, the wavelength changes, the energy changes, what else? How do we perceive that with our eyes? Not the brightness. The color. Change the frequency, you change the color. You shift along on the EM spectrum. Yes? So if we start with red, if we increase the frequency, we turn to green. Increase the frequency further, you go to blue. Increase it further, you get to UV, etc. So we see that as a change in color, not in the change of brightness. So the photon theory, if we talk about light as photons, by increasing the brightness, we are increasing the number of photons being emitted by the light source. So a bright light, even if it's at the same color, a brighter light is emitting more of these things called photons. Which is, sorry, say that again?
So it's brighter, it just means there's more of them.
There's more of them, there is not a higher frequency. However, in the wave theory, again, if you make the light brighter, you haven't changed the frequency. Because it's a wave, you've increased the amplitude. But the end, that, yes, exactly. So that still means that the wave carries more energy if the amplitude is more. Yeah? So the wave theory says that the kinetic energy, and also the time delay for that matter, should depend on the amplitude, which is the brightness of the light. So let's write this down. The kinetic energy depends on the intensity of light and the intensity is the amplitude of the wave. For the photon theory, the kinetic energy only depends on the frequency of light. It does not depend on intensity. So again, when they did this experiment, they saw that this was true, the photon theory's explanation, and that the wave theory was wrong. Yes. So again, it didn't matter if you made the light more bright, so you had a red, you make it even more bright, you make it a very, very bright red, makes no difference. The gold leaf still did not collapse. You give it lots of time, it doesn't matter, the gold leaf still did not collapse. You change the frequency so that it's above the threshold frequency and instantly the gold leaf collapses. We'll start a new page. And this is the Einstein photoelectric equation. So go back to previous knowledge that you've got about waves. And you recall the wave speed equation. C equals to F lambda. So, let's remember that C equals to F lambda. This is the wave speed equation. So we've got frequency measured in hertz. We've got wavelength measured in meters. And we've got the wave speed. Now in this case, the wave speed is just going to be the speed of light. Which is equal to 3.00 times 10 to the 8 meters per second. So the equation actually for the energy of photon tells a story. It's Einstein's photoelectric equation. So the energy of the photon was given to the electron. The electron uses a certain amount of energy to escape its well, and whatever energy remains from what it had from the photon, it then uses as kinetic energy. So we write this down as a sort of story that happens. So the photon energy, which is absorbed by the electron, liberates the photoelectron, liberates the photoelectron, and gives it kinetic energy. So here we can write an equation. The equation E, this is the energy of the photon, is equal to the energy required to escape that material. We use the Greek letter phi, plus kinetic energy. So the energy required to escape the material plus the kinetic energy of the electron gives us the total energy of that photon. This energy, phi, we call the work function, and we'll write that down in a moment. But now, how do we know what the energy of a photon is? Well, this was given in the particle physics chapter as an equation. Good. E equals to hf, or what's another form of that equation? E equals to hc over lambda. H is called Planck's constant. So, E is equal to hf, or hc over lambda. Put a box around that equation. And we'll label this as the photon energy. And we'll also recall that H is called Planck's constant. Which is equal to 6.63 times 10 to the minus 34 joules seconds. So this now will give us two versions of Einstein's photoelectric equation, because now we know what the energy of that photon was. So we simply substitute either hf into E, or we substitute hc over lambda into E. And when we do that, we get two new equations. hf equals to phi plus ek. That's one version. Or hc over lambda equals to phi plus ek. That's our second version. These are Einstein's equation. So they're both the same equation, just different forms of it. And now we can write a definition for phi. Phi is called the work function. And I'm going to underline that because that's an important word that you need, of the material. And that means it's the minimum energy required to liberate a photoelectron. Put a box around that statement. You must be able to recall this in an exam. So now the question is, if work function is an energy, the minimum energy, what would the units for that be? In joules or electron volts. So this is measured in joules or electron volts. Right, before we end lesson 1 on the photoelectric effect, we'll also do a short example. And I'm going to need your help on this one with your calculators. So make sure your calculators are ready. So we have some metal. And we have some photons that are incident on this metal. And the wavelength of these photons is 635 nanometers. And that causes a photoelectron to be liberated with kinetic energy 1.5 times 10 to the minus 19 joules. So we'll break this down into 3 questions. A. What is the photon energy? B. What is the work function of the metal? And C. What is the threshold frequency of the metal? So we start with A. What is the photon energy? Well, we know that the photon energy is given by E equals to hc over lambda. So first, we always write down the equation. Before anything else, you must always write down the equation. So E equals to hc over lambda. Next, we substitute our values and convert any values if we need to. So in this situation, you've got the wavelength of the light in nanometers. We have to convert that to meters. So H is 6.63 times 10 to the power of minus 34 times by the speed of light, which is 3 times 10 to the 8, all over the wavelength, which was 635, times by nanometers is times 10 to the power of minus 9. So put that into your calculators. What number do you get? Huh? You could. You could. But why do that when you could just put that straight away? Less thinking involved here. 3.1 times 10 to the power of minus 19 units. Joules. Okay, that's part A done. So part B says, what is the work function of the metal? Now, we were given some kinetic energy. So we just need to use the formula. So we've got E, energy of the photon, is equal to phi plus Ek. So if we want to work out phi, we have to rearrange this equation. So we get phi equals to E minus Ek. And then we put our values in. So we got 3.1 times 10 to the power of minus 19 minus 1.5 times 10 to the power of minus 19. That gives us, good, 1.6 times 10 to the power of minus 19 joules. That's our work function. And part C asks for the threshold frequency. Now, the threshold frequency is the minimum frequency. That means that to get the minimum frequency of light, we need to have light that is exactly the minimum energy required. So that means that we take it as the work function being equal to the photon energy. So that is a photon that can only liberate the photoelectron. It cannot give it any kinetic energy on top. So we say that E or HF is equal to the work function. We rearrange this equation to get frequency. So F is equal to phi over H. We put our values in. So 1.6 times 10 to the power of minus 19 all over 6.63 times 10 to the power of minus 34. So our threshold frequency is equal to what? 2.4 times 10 to the power of units, hertz. And that's the end of 2.2.1, lesson 1.